All right, so this is another thing that probably won't be new to most of you. What we're going to do is play around with what it looks like when you invert a function. So we're going to be able to determine the equation that represents the inverse of a given equation, and we're going to be able to determine whether or not a function is one-to-one, and that's pretty important in figuring out if you can invert a function in order to get another function. So first of all, we're going to start with just this basic function f of x here, and we're going to list the points within the domain. Remember that domain means your x values of the function f. So that would be the point 0, and if I plug in a 0, I'm going to have 0 plus 3. So the point 0, 3 is is within this function over that domain. The point 1, if I add 3 to 1, I get 4. And I can keep going. 2, 5 is in the domain. 3, 6, 4, 7, and 5, 8. So we've done what they asked us to do. Those are all the points that are within this domain of this function f. Okay, so there are other points, right? F also, you could plug in a 0.2 or a 1.75. But we're only listing the integer points just to get our point across here. So now what we've been asked to do is to list the points included in the inverse function f inverse of x. That's what that means. So that's some notation we want to be aware of. F negative 1 is f inverse of x. That's what this notation means. So when I say f inverse of x, I'm referring to this notation of f with a little negative 1 denoting that it's an inverse. When we have the inverse of a function, what we're going to do is we're going to take each point within the domain of the function and we're just going to flip them. All right, so the first point here, the point 0, 3, if I want a point that's within the inverse, the first point that I could put here would be the point 3, 0. All right, that's a point within the inverse function. And the next point would be the point 4, 1, 5, 2. So notice that what I'm doing here is I'm just taking each point in the original function and I'm flipping the x value for the y value and vice versa. So now I have all the points given in the inverse. So let's make a note of what we just did over here so that we know that in the future that's something that happens with inverse functions. So I'm going to put this into a language that helps me remember it. All the points in the inverse of function have the coordinates reversed. So if in f I have the point x, y, then in f inverse I would have the point y, x, because my coordinates have been flipped around. All right? So now let's see what that looks like when we actually graph a function. So we're just going to sketch this thing lightly here. Just a rough coordinate plane. And we need to go from 0 to 10, I think, on both axes. All right, we can start plotting these points. And I'm going to plot the original function in red, and I'll plot our inverse function in black. Okay, so we've got the point 0, 3, that's there. We've got the point 1, 4, 2, 5. All right, and these points just continue. They may not be perfect here, but this is basically what we're dealing with in our f function. And in our f inverse function, we've got the point 3, 0. We've got the point 4, 1, 5, 2, 6, 3. It goes like that. All right, and remember that this is continuous, so there are points between these points. We would not be wrong to connect these points and send them in both directions. It would not be a mistake. These look pretty similar. And if you continue this along, they will eventually intersect. But the point that we want to make here is that each of these functions are reflections of the other, but not over the x-axis and not over the y-axis. They are actually reflections of each other over this right now invisible line, which is the parent function of linear functions, y equals x. So what an inverse actually is it's a way to reflect one function over that line y equals x to get a new function. So let's define that here, because that takes our definition of an inverse one step further. All right. So now we know that that's what we're doing, right? If you have a point that's in an original function and I tell you to reflect it over the line y equals x, you can just flip those coordinates. And if I say you have a set of points that represents a function, what are the points that represent the inverse of that function? Just flip all those points and you know that what you're really doing is taking a function and reflecting it over that line y equals x. So what we need to do now is we need to prove that a function that we have is the inverse of another function. So this is going to take a little bit of backing up, and I'm going to use the functions that we've created up here for a minute. I'm going to make a function map. So here's f inverse, and I'm just going to make a space where all the points that exist in each could exist. If I plug in and I think it's wrong for me to maybe call this f inverse. I'm just going to call this is just going to be a map of f. All right, these are my inputs, and this is my f of x. All right, we'll back up. If I plug in a 0 to my f of x function, my output is 3. So I know that a 0 will yield a 3. And if I plug in a 1, I get a 4. And I can keep going. A 2 gives me a 5, right, and so on. Okay, so the relationship that exists with f inverse of x, and I could kind of relabel this if I want to, and I could call these my x values and these my f inverse values, because if you look at plugging in a 3 into my f inverse function, that gives me a 0 as an output. So a 3 as an input gives me 0 as an output. And in my inverse function, 4 as an input gives me 1 as an output. And 5 as an input gives me 2 as an output. So what you see here is that if we combined these functions, like we did in class today, and we had f of f inverse of x, we would end up exactly where we started. All right, for example, let's say we wanted to do f of f inverse of 3. Okay, well, I would start with the innermost function here. What is f inverse of 3? Well, I could look at my map, I could look at my points, whatever I want to do. But if I plug in a 3 to my inverse function, that gives me a 0. Okay, so that's the same as having f of 0, because f inverse of 3 is 0. Well, what is f of 0? If I plug in a 0 into my f of x function, that gives me a 3. So I end up with a 3. Let's try this one more time, and we'll do it with the reverse. If I have f inverse of f of 2, well, what is f of 2? According to my function map and to my points, f of 2 is 5. So that means that this is really just f inverse of 5. Well, what is f inverse of 5? If I plug in a 5 to my inverse function, I end up with a 2 again. So the identity that we've kind of uncovered is that anytime you take f of f inverse of an x value, you will get x. And this is an identity that we want to hang on to. So if you have a function and its inverse, and you compose those two together, you should get exactly what you started with. So let's prove that that's what's going on here with these two functions. We've got y equals 5 over x plus 2, and we want to see if that's the inverse of this function. So we could test it with a number, all right? So let's plug a number 1 into this function. Okay, so we're going to have 5 over 1 plus 2. And 5 over 1 is 5, plus 2 is 7. So if I want to see if this is the inverse, I'm going to take that 7 and I'm going to throw it into this function. And if I get 1, then I've proven, or it's likely, that they are inverses of one another. So I will have 5 over 7 minus 2. 7 minus 2 is 5. 5 over 5 is 1. So right now it's looking pretty good, because what I just did is I composed these functions together and I got exactly what I started with. But I only tested one number. So the last thing I'm going to do is just test and see if I get it without plugging in any numbers. So I'm going to start with this function. Why don't I call this function g, just to make it look like what it's looked like in the past. And I'll call this function g inverse, because right now I think that they are inverses of each other. I'm going to set this up as g of g inverse of x. So what we need to do is we need to compose these two together by putting the inverse function inside of the original function. This will be a little bit tricky because it's going to involve some fractions, but we'll be able to do it. So my original function is 5 over x plus 2, and I'm leaving that space blank because that's where my inverse function needs to go. So in my denominator, I'll have 5 over x minus 2. And if this becomes x, then I've proven that they are inverses of one another. Okay, let's think of a fraction rule here that'll help us. Instead of dividing by this fraction, I would much rather multiply by the reciprocal of this fraction. So I'm just applying that rule from algebra. I'm going to have 5 over 1, and instead of dividing it by 5 over x minus 2, I'm going to multiply it by x minus 2 over 5. And I still have a plus 2 on the outside. So let's deal with what's inside the parentheses here. When I multiply these two things together, actually these 5's will cancel, because 5 divided by 5 is 1. So I'll just be left with x minus 2 over 1 plus 2, and that just equals x, because again we have some cancellation that's going to happen here. So what we've just proven is that when I compose these two functions together, I get whatever I started with. So I will say, therefore, both functions are inverses of each other. And that's as far as we're going to take it in this video. We'll pick up right where we left off tomorrow.